Questions about anything? So homework 4, that's a 2-week homework that's due this tomorrow, Thursday, at 11:30 p.m. in Gradescope. I've posted practice problems on the home page now for exam 1, which is next Wednesday in class. I'll bring paper. All you need are pencils and erasers. And there's more information about the exam on the home page. So the practice problems are basically old exam questions. One is an old exam, and the other are practice problems, mostly from old exams. A couple of them are longer than a typical exam question because they're just so good for review. A couple of those were from take-home exams. Anyway, they're good problems to practice on. And of course, if you ask questions about the problems on Piazza, I can address them there. And maybe it's fine to work together on some of those problems on Piazza. Were there any questions? Let's see. I promised I'd prove Schwarz lemma today, which is a very important result. Simple to state, but has broad implications. So it says that if it's about analytic functions that map the unit disk into itself. And a further condition that's important is that it fixes the origin. F of 0 equals 0. We're going to study conformal mapping, which are one-to-one onto analytic maps between regions. Turns out analytic mappings preserve angles, and that makes them conformal. And this is a key lemma in understanding those things. And it's a key lemma in the proof of the Riemann mapping theorem. So it's going to be something with us the rest of the semester. Anyway, it says that if we had such a mapping, then it would have a growth condition that it has to satisfy. Namely, the modulus of f of z is less than or equal to the modulus of z for all z in the disk. That's true at 0 because they're both 0, but it's true everywhere else too. And the modulus of the derivative at 0 is restricted to be less than or equal to 1. So that's part 1 of the Schwarz lemma. Part 2 has to do with what happens if there's equality in either of A or B. Well, A is true at 0, so that equality doesn't count. But if that inequality is an equality for a z that's different from 0 in A, or if the inequality in B is an equality, so f prime of 0 is equal to 1 in modulus, then the mapping has to be a very specific type, namely it's a rotation. So if equality holds in A for some z unequal to 0, or in B, then f of z is lambda times z for a unimodular constant lambda. And if you write lambda as e to the I theta, which is on the unit circle, then you see that that's just a rotation by an angle theta. So that's a very special kind of map. Okay, and the proof is going to be rather straightforward and easy. It's basically just the maximum principle, but we're going to apply it in a clever way. Let's see, that inequality A has f of z on one side and z on the other. If I were to divide by z there, I would get f of z over z is less than or equal to 1. That would be my target inequality. And so f of z over z is a natural thing to think about. If I divide both sides in that inequality by z, I would have f of z over z if z is unequal to 0. But if you think about that, that is a difference quotient basically. So I would write f of z over z. Remember, f of 0 is 0, so this is f of z minus f of 0 is 0 over z minus 0. That's a difference quotient. And we know the thing is analytic, so as z tends to 0, this is going to tend to f prime of 0 if z is equal to 0. Okay. That function has a removable singularity at the origin because it's continuous there. So the Riemann removable singularity theorem implies, I guess I should say f is continuous at the origin. Continuous at z equals 0. So the Riemann removable singularity theorem implies 0 is removable. A removable singularity. So f is analytic on the unit disk. And now the next thing we're going to think of is the maximum principle. And if you think about it's tempting to think about the unit circle. On the unit circle, modulus of z would be 1. And f maps the unit circle, the unit disk into itself. So the modulus of f of z would be less than or equal to 1. And so we'd get maximum principles would say that thing has modulus 1 on the unit circle. And so we'd get the Schwarz lemma from the maximum principle. Unfortunately, we don't know that f extends in any sense up to the boundary. There's no reason to think that it's continuous up to the boundary or even defined on the boundary. So, can't do that, but that was a really good idea. And so here's what Schwarz did to get around that. Okay. So I'll pick any old z naught. Let z naught be in the unit disk. And then pick an r. Pick a radius. R with the modulus of z naught less than r less than 1. So I'm just making a disk so that the disk of radius r contains z naught and it has radius less than 1. Well, then the maximum principle for that disk is perfectly, the maximum principle would tell us that f of z naught is less than or equal to the max of, as z is less than or equal to r of f of z, of course. And that the maximum principle tells us that max occurs on the boundary. So that's equal to the max of mod z equals r of f of z. And let's see, remember f of z is equal to f of z over z. Okay, let me put some modulus here. Modulus, and that's let's see, that's equal to modulus f of z over modulus of z. That modulus, so I'm going to do when z equals r. When z equals r. So this is going to be equal to, this is less than or equal to 1. F maps into the unit circle. So this is less than or equal to 1 over z. And that's equal to 1 over r when mod z equals r. So let's see, I'm thinking here, mod z equals r. So it's not the origin. So it's that value of f of z is not f prime of 0. It's f of z over z there. Okay. So the aha moment is, I would have f of z naught is less than or equal, this is actually less. right? Because f of z is less than 1. It maps into the unit disk. So that's a less. So it's less than 1 over r. And now you think about how I chose that r. It just had to be any old thing between those two values. And you realize, oh, I wanted to use the unit disk, but I can squeeze that r out to 1. If I squeeze 1 over r would slide down to 1 as r slides up to 1. And so that's the brilliant idea. We're going to let r slide up to 1. And we get that f of z naught is less than or equal to, let's see, they're all less than 1, so when I let it slide down, I can only conclude that this is less than or equal to 1. It could definitely be 1, because all those 1 over r's are bigger than 1, and so they're squeezing down, and I can't rule out the possibility that maybe f of z naught was equal to 1. Okay, well that gives me a and b. So z naught was arbitrary. So we see that the modulus of f of z is less than or equal to 1. And that implies a and b. And now the part b of the second part, part 2, if there's equality in A or equality in B, that means that the equality in A for z naught unequal to 0, or equality in B, let's see, what would that imply? That would imply that f of z naught has modulus 1. Equality in B would imply that f of 0 equals 1 in modulus. Okay, and so that means the maximum modulus is assumed on the inside. So that would be a local max. We see the modulus of f of z assumes a local max. At z naught inside the unit disk. And so the other version of the maximum principle would imply that that thing is constant. And of course that constant would be equal to f of z naught, and that's unimodular. That's the unimodular constant lambda. And so we see that for z unequal to 0, we'd have that f of z is equal to f of z over z, and that's equal to lambda. And so we see that for z unequal to 0, we would have f of z equals lambda z. That's also true at z equals 0. So this is true at z equals 0 too. So check. That's how we conclude. Questions about that? Okay, well that's going to be useful and important later on. I thought this is kind of a good place to, since we've been talking about log and essential singularities, this is a good time to think more about how we cook up log functions and roots. So logarithms and roots on a convex open set. Or more generally, on any domain where the Cauchy theorem holds. Any domain where the Cauchy theorem holds, namely the integral around loops of analytic functions is 0. If we can do it on a convex set, then the basic idea is going to work in general. Okay, so to get rolling with this, there's a way of thinking here. Let's say I have a non-vanishing analytic function. That's important because you can't cook up anything so that e to the z is equal to 0. So it's got to be a non-vanishing function to have a complex log. And we're looking for analytic log functions. So we've given a non-vanishing analytic function. I'll call it capital F of z on a convex open set. Convex open omega. Domain omega. Okay, so we're going to think we want an analytic G with f of z equals e to the g. If we had such a thing, so here's thinking out loud. If we had G, I could differentiate that equation, and I would get f prime of z by the chain rule is e to the g of z times g prime of z. I stare at that for a little while, and it occurs to me, I can divide that equation by, here's what I'm going to do. I'm going to divide by f of z. And f of z is e to the g of z. And so this is the basis of logarithmic differentiation, basically. Notice that the e to the g's cancel on the right-hand side. So, what do I have? I have that, I'll write it like this. G prime of z is f prime of z over f of z. That's a candidate for how to find that. That's a brilliant idea for how we can find the g we want. G, if it exists, is an antiderivative for f prime over f. So a candidate for G is an antiderivative and we know how to do that on a convex open set. So an analytic antiderivative for f prime over f. Okay, so that I was just thinking out loud here. So this is me thinking. But now I'm just going to do it. So now here's the proof. Let's define let's see, I'm going to define my g of z. Remember how we cooked up antiderivatives? We took a line integral from a fixed point a to z, and we want to find an antiderivative for f prime over f. Okay. And we know it's an antiderivative. So that's it. This a is fixed. And z is allowed to move around. We know this is an antiderivative. So we know g prime is equal to f prime over f. Good thing that f is not vanishing, so that there's no danger of that thing being bad. Okay. And so the question is this g going to work? Is e to the g equal to f? If you think about it, it's almost. So let's see, why is it? It's almost. Let's see, I'm going to look at e to the g. I'm going to look at f over e to the g. So I take f and I divide by e to the g. That's going to turn out to be a constant. And in fact, if I differentiate it, d by dz of this, let's see, when I differentiate it, I'd get an e to the g squared in the denominator and use the quotient rule. Let's see, I'd get an f prime of z, f prime times e to the g, minus f times the derivative of e to the g. And the derivative of e to the g is e to the g times g prime. And that g prime is f prime over f. And when I put that there, the f's cancel and I get f prime minus f prime in the numerator. And so that's a big fat 0. So it's not 1, but it is constant. I mean, it might be 1. Be lucky if it was 1. Okay, by the way, we need omega. We need a domain. I guess convex sets are domain. So to deduce that this thing is constant, we need this thing to be a connected set. So later on, I'm going to say I need a domain to do this. So f over e to the g is a constant, c, on our convex omega. Let's see. So think about that. I've got f as a constant times e to the g. And I kind of want f to be e to the something. So a trick here is, let's let b be a log of c. By the way, c is not 0 for sure, because f is never 0 and e to something is never 0. So note that c is not equal to 0. Yeah. Okay, so then I would have f is c times e to the g, and that would be equal to, c would be e to the b. And I know that logs satisfy this sum rule, b plus g, and that's b plus g is the thing I wish I started with. All right, that's what I want. This is it. That's a complex log. Complex analytic log of f. The b plus g is. Questions about that? Okay, and now I'm going to show you the standard trick. What if omega is just satisfies a domain that satisfies the Cauchy theorem? You do exactly the same thing. You just don't have lines to use in that formula. You would define, I'll say define in quotes, define g of z would be an integral from a to z, a curve that starts at a fixed a and goes to z of f prime of w over w dw. And step one is to show it's well defined. It's well defined. And that's easy because if I took two curves, so I could always go from A to Z along gamma. And if my other curve was a gamma twiddle, I would go the other direction, minus A to Z twiddle is closed. So if I took a different curve, that would give me a closed curve, and the Cauchy theorem would imply that g of z equals g of z twiddle. Because the integral around a closed contour would be 0. Okay, so that's the easy part. But then the next step would be to realize that now I realize it doesn't matter what curve I take. I can localize. So let's see, I'll draw the picture I drew in a previous iteration of this. So let's say I want to know its analytic right here on this disk. Let's call that a Z naught at the center. Well, I would take a curve that starts at A and goes to Z naught. There can be holes in this thing. No, I don't want any holes because I want Cauchy theorem to hold. And then I would take the straight line that goes from Z naught to Z. That would be the line here. Call that L. This is a Z. And so my gamma from A to Z would be a gamma that goes from A to Z naught, followed by the line that goes from Z naught to Z. And then we would get from this, so that's step 2, I would get that G prime equals F prime over F on that little disk. And so G would be analytic and it would have the right derivative. And then I could do that routine. I would get that. Step 4, repeating the previous thing, I would get that F is equal to e to the b plus g on that disk. But the fact that it's a domain, the identity theorem finally extends to hold on the domain. We need a domain. By the identity theorem. Okay, and you'll notice I used the word logs and roots in the beginning of the today. It turns out whenever you have a log like this, you get a root. So a fact is, analytic logs, log functions, give rise to roots. Root functions. And that's a no-brainer, and the reason why is, let's see why. So let's suppose f is non-vanishing. Analytic. Then we have f of z is equal to e to the g of z. And the aha thing is, if I wanted something whose nth power was f, so here's how you see, let's see, f of z, I want it to be equal to something to the nth power. And if you think about what you need to put there, you put e to the g of z over n. And so that's an analytic nth root. Of f. That's how you do it. Okay, any questions about this so far? Well, let's see, I'm going to do something fun now. Kind of a mind-blowing thing in complex analysis called the argument principle. But before I do that, there's something I should have defined. I've been using this word, letting it slip out from time to time. Let's see, at a pole, Z naught is a pole of f of z, we know, let's see, we know a couple things. We know the pole has an order. We know that f of z equals z minus z naught to the minus n times the f of z, where f of z is analytic. And f of z naught is unequal to 0. And when we play games and we write this out, we would get an a naught over z minus z naught to the n plus blah, blah, blah. Let's see, that a sub n minus 1 over z minus z naught. And the rest would be a regular power series. And this is the principal part. And we know the principal part is unique. And the thing I should have defined at the moment when I did this the first time is that this number right here turns out to have importance. It's called the residue. So the an minus 1, the coefficient on top of z minus z naught, is the residue of f at z naught. And we write an minus 1 equals residue at z naught of f. This is the thing that's going to appear in the residue theorem soon. In fact, right now. Well, a great fact at a pole, or let's see, at a 0, I'll kill this two things with one. At a 0 of multiplicity n, or order n, or a pole of order minus n, the residue is the residue of f prime over f of f prime of z over f of z, that thing that appeared in my calculations above, the logarithmic derivative, the residue is, for a 0, it's n. For a pole, it's minus n. So see the pole of order n, the residue is minus n. And I can prove those with exactly the same calculation. Let's write proof. Let's write f of z equals z minus z naught to the n times f of z. So n positive, that's a 0. N negative, that's a pole. So we noticed this dichotomy earlier. And so now if I calculate f prime, I use the product rule. This works even if n is positive or negative. Same formula, doesn't matter. Product rule, z minus z naught to the n times f prime of z. Now, like I did in that proof above, I'm going to divide by f of z. And let's see, f of z is z minus z naught to the n. And we see, aha, f prime over f, the logarithmic derivative, that f of z is going to cancel out, and it's just going to give me n over z minus z naught. That's called a simple pole of order 1. And there's the residue staring me in the face. Now let's see what's left here. What's left is something analytic, namely f prime of z over f of z. This is non-vanishing. So this stuff is analytic. And this is the principal part. And this is the residue. And sure enough, when it's a 0, that's a plus n. And when it's a pole, that's a minus n. So that's how you see that. Well, this observation leads to this famous theorem. I'm going to do it for a disk because it's amazing how much mileage we would get out of this thing, just even for a disk, kind of like the Cauchy integral formula. So this is the argument principle. For a disk. let's suppose f is analytic on a disk. I'm going to do the first version just to count zeros. There are more sophisticated versions that count zeros with pluses and poles with minuses. I'll state those eventually, but today I'll start with just zeros. On a disk of radius r about z naught, and let's suppose that I've got another radius, 0 less than little r is less than capital R. And let's suppose f has no zeros on the smaller circle, has no zeros on the circle of radius little r about z naught. I guess I've used this a lot. This is the z, such that z minus z naught equals r, the circle. Then we can count the zeros inside that circle, 1 over 2 pi I. It's like the Cauchy integral. Integral around that little circle of f prime of z over f of z, the logarithmic derivative, dz. That's equal to the total number of zeros of f inside the little circle, counted with multiplicity. Number of zeros of f inside that circle, counted with multiplicity. So if it's a double zero, it gets counted twice. Triple, it gets counted 3 times, etc. Multiplicity. Okay. Oops. Well, the proof is going to be a snap. I feel like I might have time to do the proof. Oh, let's see. I guess if I'm going to count something, I better make sure there are finitely many of them. So a thing to note, f can only have finitely many zeros inside there. Why is that? So have finitely many. Zeros, I'll call them z1, z2, out to zn in CR z naught. Or I'll call it in the disk of radius r about z naught. There's no zeros on the circle. Why can there only be finitely many in the inside?
If they're infinitely many, you can just keep bisecting.
Right.
Get a convergence sequence.
Exactly. That's how you prove the that famous analysis fact. That if I make that closure, so the closed unit, the disk of radius r, is a compact set. And so if there are infinitely many of those things, they would have a limit point in the compact set. What's that theorem called? Heine-Borel, maybe? I never remember the names. I just remember the theorem. Even though I proved it last semester in 341. Yeah, so I guess I should say the closure is a compact set. And of course there's no zeros on the circle there. It's compact. Closed and bounded meaning. Infinitely many would imply they have a limit point. Of course, the limit point, that would imply the limit point can't be on the circle. Can't be on the circle. Because the limit point of a zeros would mean it's also a 0. And there are no zeros on the circle. So, I guess limit points of zeros are zeros. For continuous functions. So it can't be on. So the zeros pile up at a point inside the disk, and the identity theorem implies the thing would be identically 0. And we're not assuming that. We're assuming it doesn't have any zeros on the circle, for example. Okay. So, let's say the say 0 zk is a 0 of multiplicity mk. Can somebody close that door? Mk. Now the idea is to subtract off those principal parts. So now f prime over f minus the sum as k goes from 1 to capital M of the multiplicities mk over z minus root k has removable singularities at all the at all those zeros at each zk. So the aha moment is when you integrate that now around the circle, you use the Cauchy theorem. Cauchy theorem yields 1 over 2 pi I integral around the circle of radius r about z naught f prime over f. That's the one we care about. This is a big fat 0 here. Minus, and here we'd have a sum as k goes from 1 to capital N, 1 over 2 pi I. I can pull the mk out in front. And what's left is an integral I'm very familiar with. 1 over z minus zk dz. And remember, that's 2 pi I when the 0 is when zk is inside, and 0 when it's outside. That was something we used to prove the Cauchy integral formula on a disk. And so check. When I put that on the other side, I see that famous argument principal integral is 2 pi i's cancel, and I get just a sum of the multiplicities. So that's what I mean by counting with multiplicity. I add up the zeros with their multiplicities. If they were all simple zeros, there'd be n of them, and this would count them, n. 1 plus 1 plus 1 n times. Done. So that's a beautiful proof. If there were some poles in there, I could do the same thing at the poles, except those mk's would be negative. So I'd count the zeros with pluses, their multiplicity, and I'd count the poles with minus their multiplicity, or minus their order. So that would be an interesting thing to play around with. And we'll do that soon. Any last minute questions about anything? Yeah.
The fact that each zk is a removable singularity, is that the same thing that we did?
Oh, it's not it's a removable singularity when I subtract off those principal parts. Yeah, so the function that's inside the integral